Now it's time to geek out with some high-tech geology, measuring absolute time with isotopic clocks. We're going to talk about isotopic dating theory, including radioactive atoms, what they are, how they can be used, parent-daughter relationship, a description of how radioactive atoms change, the half-life, the rate at which this change occurs. Henri Becquerel was a French physicist. He won the Nobel Prize in 1903 as one of the discoverers of radioactivity, along with his graduate students Marie Curie and Pierre Curie. So they all took home the 1903 Nobel Prize in physics. Marie Curie went on to win a second Nobel Prize later on for her work in refining radium. Coming up soon, it'll be 99 years since Marie and Pierre Curie successfully isolated radioactive radium salts from a mineral called pitchblende. This was done in their laboratory in Paris. In 1898, the Curies discovered the existence of the elements radium and polonium in their research on the mineral pitchblende. This pitchblende is dominantly made up of uranium minerals. 1 year after isolating radium, they'd share the 1903 Nobel Prize in Physics with French scientist Henri Becquerel for their groundbreaking investigation of radioactivity. Marie Curie was born Marie Sklodowska. I'm not very good at Polish, so that's as good as it gets for me. In Warsaw, Poland in 1867. She was the daughter of a physics teacher and a really good student. She ended up studying at Sorbonne in Paris, graduating with high honors. She received a degree in physical sciences in 1893 and mathematics in 1894. That year she also met Pierre Curie, a French physicist and chemist who had done important work in the study of magnetism. They were married in 1895 and remained married until Pierre's death, tragically, just a few years later. So while discussing a topic for her doctoral thesis, Curie began studying uranium, which was really the basis of Becquerel's discovery of radioactivity in 1896. This term, radioactivity, which is related to the phenomena of radiation caused by atomic decay, was coined by Marie Curie. She made up that term, or she coined that phrase, radioactivity. In her husband's laboratory, she began studying the mineral pitchblende and reported the probable existence of one or more radioactive elements in the mineral. Pierre Curie joined her research in 1898. They discovered polonium, named after Marie's native country, Poland, and radium. While Pierre investigated the physical properties of the new elements, Marie worked to chemically isolate radium from pitchblende. Unlike uranium and polonium, radium does not occur freely in nature. They spent many months refining several tons of pitchblende to isolate 1/10 of a gram of pure radium chloride in 1902. At that point, radium was probably the most valuable substance on Earth by weight. On the results of this research, she was awarded her Doctorate of Science in June 1903, and later in that year shared the Nobel Prize in Physics with her husband, Pierre, and Henri Becquerel. She was the first woman to win a Nobel Prize. Pretty good year. Get your PhD and win a Nobel Prize in the process. Now, originally, she wasn't going to receive a Nobel Prize. It was going to go to Pierre and Henri because they're guys, and that's what guys do. They actually lobbied on her behalf that she be included, so kudos to them. Even though she did most of the work, she was able to get credit for her work. Pierre was appointed to the chair of physics at the Sorbonne in 1904, and Marie continued working on isolating pure non-chloride radium. In 1906, Pierre was killed in an accident in Paris, and Marie continued her work. In May 1906, she was appointed to her husband's seat at the Sorbonne and became the university's first female professor. In 1910, she succeeded in isolating pure metallic radium. For this achievement, she was the sole recipient of the 1911 Nobel Prize in Chemistry, making her the first person to win a second Nobel Prize. I think to this date, she's the only person to win Nobel Prizes in 2 different fields. She became interested in the medical applications of radioactive substances, working on radiology during World War I, and the potential of radium as a cancer therapy. That turned out to be a mistake. So this radiation, discovery of radiation, was really a magical thing. You could see through people with it. And lots of people were using it for lots of things. Some good, some bad. People were making everything they could think of out of radium. Not pure radium, obviously, but finely disseminated radium. So water for curing your digestive problems. There's a really terrible story related to radium, the early use of radium, called the Radium Girls. And you can Google that if you've got the stomach for it. But it's when people adopt something before they understand it. An example of that. And ultimately, Marie Curie died in 1934 from leukemia caused by her 40 years of exposure to radioactive substances. She would carry radium around in her pockets, and people had these substances on their desks because they emitted a nice blue color, glowing in the dark. And that ultimately killed a number of these early researchers. Ernest Rutherford and Frederick Soddy came along shortly afterwards, working at McGill University in Canada. Continuing their work on radioactive materials, they concluded that radioactivity was a spontaneous transmutation of atomic elements, something that happened naturally without the interference of humans. In the course of radioactive decay, an element breaks down into another, less massive element, releasing alpha, beta, and or gamma radiation in the process. The pair also determined that a particular isotope of a radioactive element decays into another element at a distinctive rate, a particular rate dependent upon the element. This rate is given in terms of a half-life, or the amount of time it takes half of a mass of that radioactive material to break down into its decay product, that is, to go from the parent product to the daughter product. In 1905, Rutherford suggested that geologists could use the concept of the half-life to date rocks, to determine the age of ancient rocks. How is this done? We use isotopic dating methods that include uranium-lead pair dating, potassium-argon pair dating, rubidium-strontium pair dating, and carbon-nitrogen pair dating. There are lots more. There are many, many different ways to do this. These are 4 of the principal techniques. And we see a chart of half-lives here for elements that are useful in radiometric dating. Uranium-238 breaks down into lead-206 with a half-life of 4.4 billion years. This means it's useful for dating material that's between 10 million and 4.6 billion years of age. The minerals that we look for to do this kind of dating are zircons and apatite. Zircon is a zirconium silicate. It's very, very, very resistant to weathering and change. Therefore, it tends to stick around for a very long time. Uranium-235 decays into lead-207 with a half-life of 0.7 billion years. Its useful dating range is 10 million to 4.6 billion. Again, zircon and apatite are the primary minerals. Potassium-40 to argon-40, half-life of 1.3 billion years. This is effective in dating minerals that range in age from 50,000 to 4.6 billion years. The favored minerals for this work include muscovite, biotite, and hornblende. Rubidium-strontium, rubidium-87 to strontium-87, has a half-life of 47 billion years. Its useful or effective dating range is 10 million to 4.6 billion. Again, muscovite and biotite are going to be important as source minerals, along with potassium feldspar. And last but not least is carbon-14 to nitrogen-14. This has a half-life of 5,730 years. That's probably worth memorizing. And an effective dating range in years of 100 years to 70,000 years. We can stretch it, if conditions are right, to about 150,000 years, but realistically, this is what we're working with. Now, the types of materials that can be dated using carbon-14 dating include wood, charcoal, peat, bone, and tissue, as well as shells and other calcium carbonates. So what's important about this is we can take an ancient human bone, a Neanderthal, that might be, say, 500,000 years old, and we could date it, except all the carbon-14 would be gone by then. So we're going to have to work with human remains that are less than 70,000 years of age. And that's cool because most of human history has occurred in the last 70,000 years. So it's important when you choose your isotope system that you know the approximate age of your sample. If we're looking at a Neanderthal, we're looking at maybe 500,000 years. So carbon-14's out. Rubidium-strontium won't work because 10 million years is the cutoff. Potassium-argon, that's a possibility. That 500,000 years is going to be between 50,000 years and 4.6 billion years. It's not a really super accurate technique, but it works. It's also important that you know the abundance of the isotope in your samples. If you don't have any uranium-238 in your sample, you don't get to determine a date for that sample. If you don't have any carbon-14 in your sample, like in a Neanderthal, you don't get to use carbon-14 to date that Neanderthal. So how does this happen? Well, if you do some simple math and add up the mass of a proton and an electron, you get pretty close to the mass of a neutron. The slight difference is the amount of energy that's released. E equals mc squared describes that. As a neutron decays, it becomes a proton and it ejects an electron. This means the number of protons have changed. So we've added a proton by converting a neutron into a proton and an electron. It's the number of protons that determine the element. Here we have a depiction of time in half-lives. The fraction remaining is on this axis. So start out with 100% our starting material. After one half-life, half of that starting material is gone. After two half-lives, 3/4 of that material is gone. After three half-lives, we have 1/8 of the original material. At 4 half-lives, 1/16, 5 half-lives, 1/32, and so on. So again, looking at this chart, we can see that some radioactive elements are going to be useful for dating very old materials, and others are going to be useful for dating relatively young materials. Thought question for this chapter: is carbon-14 a suitable isotope for dating geological events in the Pliocene epoch? The answer is no. It happened far too long ago. There's no more carbon-14 left. It's all decayed away since the Pliocene. How does determining the ages of igneous rocks help to date fossils? Well, you date material that's around the fossil. If you date an igneous intrusion, you know that intrusion came after the sedimentary rock that it intrudes. By looking at multiple intrusions, you can define the age of a given sedimentary sequence, therefore define the age of the fossil. Geologic time, as we saw in part 2, is broken down into a number of components. We have 4 eons, the longest periods of geologic time. The first one is the Hadean, named after Hades or Hell, and it's represented by the early bombardment period of the Earth. The Earth was getting bashed and harassed continuously by asteroids, comets, and meteors during this period of time, from 4.56 to 3.9 billion years of age. Giga-annum, Ga means billion years of age. Then we have the Archean, the ancient period. This is when we have our first continents and earliest life. This ranges from 3.9 billion years ago to 2.5 billion years ago, about when oxygen starts to appear in the atmosphere. Then we have the Proterozoic, earlier life. This is when modern tectonics and our climate system become modern, and oxygen begins to rise in fits and starts. There's oxygen, then no oxygen, then oxygen again, then no oxygen. Then we have the Phanerozoic, visible life. This is when we have development of multicellular animals and plants, and ultimately all modern life. This ranges from 542.5 million years ago to, January 28th, 2021. And here we have a representation of this time in several different resolutions. We have the eons listed here. We're going to take a closer look at the Phanerozoic eon, visible life eon, and then we're going to zoom in further and look at the Cenozoic era, the modern life era, and then into the epochs here that we discussed at the end of the last lecture. These have now been defined and characterized in precise terms using absolute radiogenic isotope dating. Other techniques that we touched upon earlier, I think in part 1, include sequence stratigraphy, chemical stratigraphy, paleomagnetic stratigraphy, and the general clocking of the climate system. So here we have a series of diagrams. We're going to zoom in on these, hopefully make sense of them. Starting out with a seismic profile. This is the return you would get from a series of geophones. These are devices that pick up vibration in the Earth's surface or in water, in case of the ocean. And by bouncing waves down into the rock or sediment, and then waiting for the return, you get a series of lines that represent the structure within that sediment or rock pile. Now it looks like this. Now this is a big part of being a geophysicist for, say, a petroleum company, generating these seismic profiles. And the first time I saw somebody working on one of these things, I said, "So what are you doing? What's the secret here?" They go, "Well, you take this colored crayon and you draw a line where you see other lines." And I said, "Okay, I thought that's what you were doing, but is that really it?" And the answer is, yes. We're just drawing lines on top of other lines. Oh, I could do that. So the result is you take those lines on the seismic chart, and if you have some basic information from a core, you can relate the seismic profile to the type of sediment or bedrock you're looking at in 3 dimensions here. And what you can reconstruct is what has happened in the past. Again, because this layering is going to occur in some order from oldest to youngest. So essentially what you're doing is reconstructing the environment as it changes through time. We can look at the paleomagnetic record as well of a sequence. And if you have a well-characterized sequence, such as this one, you can develop other sequences in either nearby or distant rock and maybe tie it all together in this fashion. So here we see a combination of magnetic or paleomagnetic reversals with some sedimentology, some chemostratigraphy in terms of the strontium isotope values of the rock, and putting it all together in this initially confusing looking diagram, we can define what's happened over the region in geologic terms as far as the environment of deposition is concerned. So the sequence stratigraphy and chemostratigraphy and paleomag stratigraphy will allow us to clock the climate system, determine when important things happened climatologically. When we look at a geologic timescale now, we've gone from relative ages to absolute ages. We now know that this Cambrian Ordovician event occurred at a precise time. We know the Paleozoic started at 542.5 million years ago. We know the end Ordovician mass extinction was 441 million years ago. This is another mass extinction that we worked on, in this case not in the Gulf Coast, but in Nevada and a couple other locations. This represents a cold period, a rapid global glaciation, and we know that happened at 441 million years ago because of radiogenic isotope chemistry. Same for all these other mass extinctions. And then I mentioned briefly that we worked on one here as well, the Eocene-Oligocene extinction in the Gulf Coast using fish ear bones. So we've now got this thing set to a clock, and we know that certain extinction events were caused by climate events, and now we can start to look at whether those climate events occur periodically, every 23 million years or 100 million years or a billion years. They don't, but we could look at that.